Okay, today we're going to jump into the last chapter of the semester, chapter 18, on electrochemistry. And as I've said before, I'll repeat myself. We won't have enough time to do a review before the exam during exam week. So I posted the latest review video I have from last summer. And you'll have to review that to iron out any problems. Of course, between now and exam week, I still have office hours, and we can connect by private session if you want. I mean, if you're still having trouble with this topic, then we can deal with it. And obviously, there's no comprehensive final. We just have chapter 18 to do, and then that's it. We're done.
Dr. Bly, I have a question.
Certainly.
Actually, I have two questions. Where is the video located on Blackboard for the review?
It should be in there with the rest of the documents.
Okay, I just wanted to make sure. And then the second question is for our lab, the final notebook check. I didn't see a place to put it because I know you normally do that.
Maybe you checked before I built it.
Okay.
When did you look?
Yesterday.
Okay, it should be there. If you check right after I sent the email, it was too soon.
Okay.
As soon as I sent the email, then I went in and built the assignment for you to load.
Okay.
If you still can't find it, then please let me know, because then there's probably some switch that's wrong in there and it's not available.
Okay.
And that'll never do.
No.
I'll tell you what.
I can look now if you want me to.
Yeah, and while you're doing that, I'm gonna share my browser and go into Blackboard and look for the video. So let's see. Okay, Blackboard, here we go. Oh, once you get into Zoom and Blackboard, it doesn't let you get back out. So I've got to go in and reopen Blackboard. There's 102. And we go down to should be under lectures and reviews. And the last chapter 18 folder. Okay, notice the dates. This was the lecture for the summer on this chapter.
Okay.
And there is the review right there.
Okay. And I did find the final lab notebook check. I'll just look.
Good deal. Okay, I'm going to stop this share, and then we're going to share the PowerPoints so we can get this show on the road. Here we go. And I need to blow it up. Come on, slideshow. There we go. Let's see. I always have to move stuff around so I can see what I'm doing. Okay. Electrochemistry. That's by my way of thinking. It's pretty much self-explanatory. It has to do with chemistry, which is, we've decided that that's the study of how substances change from one to another. And then electro just means that electrons are involved. But there's a formal definition. It's actually the study of the interchange of chemical and electrical energy. So you do have to have electrons transferred during a reaction. And there are energy transfers as well. You still have, in a balanced equation, you still have equal masses in reactants and products. That hasn't changed. But underneath, one of the driving forces for the reaction is the movement of electrons. So why would we want to be interested in the movement of electrons? Well, aside from the purely theoretical and being able to describe the nature of the chemical bond, there's also a practical motivation for studying the movement of electrons in a chemical reaction. One is if we can get at them and there's this energy that they're transferring, we might be able to tap into it. So we got to figure out how to access those electrons, and we'll do that over the course of this lecture. We need some terms, though. We need to understand what the terms mean. When we say an electrochemical type reaction, it's usually described as an oxidation reduction. And short for that is redox. Don't ask me, well, I know why it's called redox and not ox-red. It just doesn't sound right. It's kind of weird to the ear. So redox reactions are those that describe movements of electrons during the chemical reaction. So what's oxidation? Anything that is oxidized during the reaction has lost electrons. Now, if they start out, say an ion starts out at a -7 charge, it could go to a -5 or 4. It could go to neutrality. It still has to lose electrons to get there. Remember, you can't mess with the protons. Only the electrons determine charge by a balance between the electrons and the protons. So that's oxidation. Reduction is just the opposite. Anything that gains electrons during a reaction is said to be reduced. And they always come in pairs. You can't have one without the other. And there's a little mnemonic device for remembering which is which. It's called oil rig. Right? Oxidation is loss, reduction is gain. And of course, when you have an oxidation, when something is being oxidized, since they come in pairs, then there's another substance that is causing that oxidation. That's the oxidizing agent. And the oxidizing agent, when it causes the oxidation, is actually drawing electrons away. So it is being reduced. So an oxidizing agent is the one that's being reduced. And conversely, the reducing agent is the one that's being oxidized because it causes reduction in the other substance. Okay. So let's look at this reaction. It's already balanced, and you can check it for yourself to see if it's balanced. It's got 8 protons, 1 manganate ion, 5 iron 2+ ions, yields a manganese 2+, 5 iron 3+. See, you had 2+ over here, now you got 3+, plus 4 waters. Now that is the balanced equation for this net reaction. I'm pretty sure that these ions don't exist free. In other words, without some balancing, cation for that one and anion for that one. So this is a net reaction. And the spectators are left out. But we can still balance it. All right, so how do we know which one is reduction and which one's the oxidation? And in this method of half reactions, you separate this one. You just split it apart, this big one, split it apart into 2 separate reactions. One describes the reduction and the other describes the oxidation. In order to do that, you need to determine the oxidation states for the elements. So I probably should have written this one up there already. So if we do that, and like that, and like that. Right? And then that yields Fe3 plus 4 waters, I believe. Okay? Remember the rules. If you have a single element and it's charged, that charge is its oxidation state. So this is 3 plus, that one's 2 plus, that one's 2 plus. Oxygens are taken as -2. So -2 times 8 is -2 times 4 is 8. We have to hold one of these out for that charge. So that means you only have to balance -7. So manganese would be +7. Oh, hydrogens, of course, they're plus. There. And water's a -2 and a +1. Okay, so now we can tell which species was oxidized and which was reduced. This iron 2 plus is going to a 3 plus. Only way you can get there is to lose an electron. So sometimes I write it like this. I just go, so I say a loss, 1 electron per iron. And if there are more than 1 iron, like this, times 5, equals 5 electrons were transferred in this oxidation step. But there has to be a reduction step to go along with it. So we look to see if there are any other species that change their oxidation number. And manganese is one of them. It goes from +7 to 2 plus. So how do you get there? Well, you add 5 electrons. 5 minuses cancel 5 of these pluses and leave you with 2 pluses. So if we do that, like that, that is gain. 5 electrons per manganese times 1 equals 5 electrons. So in a balanced equation, in a balanced redox equation, not only the numbers and types of elements balance on either side, but the number of electrons transferred must balance also. Now, when we write the complete redox reaction like this, you don't see the electrons, because if you gain them on one side and lose them on the other, they cancel. But for later, when we start doing some calculations, you need to know how many electrons were transferred. So during the balancing process, sort of maybe jot down how many electrons moved. Okay. Notice that hydrogen didn't change, oxygen didn't change. It's just manganese was reduced and iron was oxidized. And then you can separate the equations. Right? Now, how do we know where the hydrogens and the waters go? Well, notice if you go from here to here, they don't need hydrogen. They don't need oxygen, either one. Iron doesn't need them. I mean, you can show oxidation with just this and this, and that's what we do right here. Oops, sorry. So the hydrogens and the oxygens stay with manganese, and the clue is there's an oxygen here. Right? So if there are oxygen on this side, there got to be oxygens on that side to balance. And then if we did that, then we've added hydrogens over here. So we got to put hydrogens back over here to balance. Okay, I'm sort of giving you clues as to the half reaction balancing method. And that's what we're going to do next. This is already balanced. It's just to illustrate that you can split the reaction into 2, and you can add them back together. Right? Add these back together, you should get that complete reaction right there. Okay. I'm going to keep track on my hard copy of where we're going. Okay, I can erase this one. We're going to use a different one for the next one. Okay, so redox reactions, some of them can be balanced fairly easily by our standard method, using that budget I showed you at the first semester. But sometimes it's a lot easier if you know the reaction is redox. You determined it's redox. It's easier to do it by the half reaction method. One reason is you may not be given all of the reactants and products, and those usually manifest themselves as water and hydrogen ions. So you may not be given those, and only the half reaction will tell you how many of them and where they go. So here's the method in step-by-step form, and we'll run through one. You set your reactants and products on the proper side, and then you do your oxidation numbers, determine which ones are the oxidation reaction, which ones reduction reaction, and split them into two. Then you go to each one, the oxidation step and the reduction step, and you balance everything except hydrogen and oxygen. Then once you've got those elements balanced, you go in and look for oxygen. If there's oxygen anywhere in one of those reactions, then you balance it on the opposite side of the arrow with water. And then, of course, when you balance it with water, you're adding hydrogen ions, and then you go back to the other side, whichever the side it may be, and balance the hydrogens with protons. Now this method, since we're adding protons, hydrogen ions, this is the acid half reaction method. There's an addition, we can make additional steps to this to balance in terms of basic solutions. And we'll get there eventually. And then once you've got those balanced, balance the electrons. Now, technically speaking, once you've got the once you've got your half reaction set up, you can balance the electrons before you do the other steps. Right? This is just more or less arbitrary, but you do have to balance all of these elements and electrons. Now, before you add them back together, you may have each individual oxidation reduction half reactions balanced, but you can't add them back together until you've got the same number of electrons in both of them. One will have electrons on one side, one will have the other side. Remember, if you're reducing something, the electrons are reactants. You go on this side, and they go into the reactant, reduce it, and then they don't show up on the other side because they're in the product. The oxidation step was the other way around. If you oxidize something, then electrons will show up as a product. So once you've written those, you need to balance the electrons. And the only way you can do that now, you can't change individual coefficients in the half reactions, because then you won't be balanced. You'll just mess up everything you've done in step 2. So the only way to change the number of electrons is to multiply the entire equation through by some constant. It doesn't have to be the same constant for each reaction, just whatever it takes to balance the electrons. Then once you've got that done, you can add them together. And then after you've added them together, sometimes during, you cancel common terms. Okay, so here's a schematic. You can take it or leave it. Schematics are useful, especially if you've got a very complex laboratory experiment and things have to happen at just the right time. Then I used to set up these flow charts for my research so that I'd be sure, and when I would get ready to do something, this side flow would come in at just the right time. and I'd have things ready. It's kind of like cooking. You know, it's all about timing and presentation. Well, chemistry is not that much different than cooking, except, you know, as they say, you can't lick the spoon. Okay, so here's an example. And we're going to do this one on the board. Let's see, maybe I'll spread it out a little bit. What's that first one? The dichromate polyatomic ion. Seven, 2 minus. And they're all aqueous. Yeah, they're all aqueous. So I'm just going to leave the aqueous out because it gets in the way. If there were any differences, if they were aqueous, pure liquids, solids, anywhere in there, then it would probably be advisable to keep the phase designators intact. That's the sulfite ion, and that yields chromium 3 plus and sulfate. Okay. All right, so this one's already done, right? That's a single element ion. That's the charge. We have to calculate the others. So here's oxygen with a 2 minus. 2 minus for the oxygen means 14 minuses. But we have to hold 2 of them out for that charge. So that means we only have to balance 12. So plus 12 balances, but there are 2 chromiums. So the oxidation state on each one is plus 6. Okay? By the way, in case you didn't know, there's a difference in toxicity between various oxidation states for chromium. The most toxic is plus 6. Less toxic is plus 3. Okay, let's carry on. Oxygen, minus 2 times 3 is minus 6. We have to hold 2 out for that. So that means this sulfur is plus 4. How about this one? 4 times minus 2 is minus 8. Hold 2 out, minus 6 balances. So that's plus 6. All right. So now we have all our oxidation states. We can split the reaction out. Okay, I like to put oxidation first. It's 6 of one, half dozen the other. So the oxidation step is going to have the one that increases its oxidation number, right? It can go low, a large minus to a small minus is still increasing oxidation number. In this case, we're going from plus 4 to plus 6 of sulfur. So here we have SO3, and I'm gonna keep the oxidation state there just so I don't have to remember it. And then that one is going to SO4 2 minus, and it's plus 6. Okay. Now the reduction step is going to be dichromate. I might put it over here. And this is plus 6, yielding chromium. Okay. Now we split them out. Oxidation, reduction. We could do electrons now, or we could go ahead and I'll stay in order that I gave it to you originally. We'll do electrons later. But notice you got oxygen here and no oxygen there. You got 3 here and 4 there. Right? So this will never balance until you account for those. We've got 1 sulfur, 2 chromiums. We've got to balance the chromiums. There we go, 2 chromiums. Now we can go to oxygen. So if that's got 4 oxygen and this got 3, we need 1 on this side. Right? 1, 2, 3, 4. 1, 2, 3, 4. Okay? That means we have added 2 protons. There we go. For this one, we have 7 oxygens. There are no oxygens over here already, so we got to have all 7 of them as water. That means 14 hydrogens. Okay? Now we can do electrons. So if this is going to +4, from +4 to +6, it had to lose 2 electrons for each one of these sulfurs. There's only 1 sulfur, so it lost 2 electrons, right? 2 minuses and a +6 is a +4. On this side, reduction will gain electrons. So many electrons we're going to add on this side. How many electrons does it take to go from +6 to 3+? 3 electrons. That's for each chromium, but there are 2 of them. So that's 6 electrons. Okay? Now we need to match them up. We need the same number of electrons in both. We got 6 here and 2 there. We can get there just by multiplying this whole thing through by 3. Right? Multiply by 3, you got 6, balanced. So we're going to say 3 here for the entire reaction. Okay, that means 3 in front of that one, 3 in front of this one, 3 here, 6 here, and 6 there. And we used that 3 up. Okay, now we can add them together. All right. We've accomplished the balancing of electrons, so we don't need to bring those down. Those balance. We can bring the others down and cancel common terms afterwards. So we've got, I'm going to put the dichromate first. And then the sulfite. And then I'm going to put hydrogens and 3 waters. Okay, now we'll go on this side. We have 2 chromiums, chromium 3+, and 3 sulfates. But we also have 7 waters and 6 hydrogens. Okay, am I still on camera here? Yeah, there we go. Okay, so notice we've got common terms on both sides. Let's see, we got 14 hydrogens here and 6 over there. So if we cancel those 6, that leaves 8 over here. Okay, we got 3 waters here and 7 waters there. So if these 3 cancel, that leaves 4 over here. And then you look to see if you can reduce to a simpler whole number ratio. Right? I always look for any that have a coefficient of 1. If you got any term in here with a coefficient of 1, you can't reduce it any further. And there's dichromate with 1. So I don't bother looking at the rest of the reaction. Okay. So the subsequent slides go through this step by step. Right? And they do all that. But I thought it's easier to follow if I do it on the board, and then this just gives you a permanent record. Okay, the final balance. Let's see if I got it right. 4 waters, 3 sulfates, 2 chromium 3+, 8 hydrogens, 3 sulfites, and 1 dichromate. Okay, we're good. It's all balanced. Okay, that was in acidic solution. Now, since I have this equation already here, let me show you what you do to balance basic solution. It's what I call the fake acid method. You balance your equation as if it were an acidic solution first. Then once you've got it in acidic solution, you convert it to basic. Now, how do we do that? Well, we add hydroxyls, OH-. So wherever you have hydrogens, you cancel them out with hydroxyls right here. So we would add 8 hydroxyls right there. That makes 8 waters. Right? OH and H, HOH, H2O, there's 8 waters. But if you add them on this side, you got to add them on the other side too. So we'll have to add 8 hydroxyls over here. Okay? Now we cancel common terms. We've got 4 waters over here, and cancel 4 of them here, leaves us 4. So that's all you have to do to convert your acid balanced equation to basic. And everything stays the same except the waters and the hydrogens changed. Right? Now you have 4 waters on this side and 8 hydroxyls on that side, instead of waters and hydrogens and hydrogens and waters. Okay, we'll get to slides that go through this procedure, but I thought we already have the equation here. Why not show you how to do it? I mean, it's really simple. Okay, here's another oxidation reduction reaction that occurs in acidic solution. So what do we do first? Well, oxidation states, oxidation numbers. That's always. Well, after you've got all your reactants and products identified as well as you can, and that's usually given to you. In fact, in this class, it's always given to you. Okay. So what do we have here? Let me see. Okay. Use this one for practice. We may not go all the way to the end, but it's the beginning. The real stumbling block is figuring out what the oxidation numbers are and then splitting the equation. After that, it's just method. So if we have this bromine and we have a manganate polyatomic, which gives bromine liquid, the others are aqueous, and then manganese 2 plus, aqueous. Then we say, remember, standard state elements are always 0 oxidation state. And there's another one right there. Here's one. So we just have to do this one, right? 4 times 2 minus is minus 8. Hold one out for that minus. So this is a plus 7 manganese. So we go from plus 7 to 2 plus. Now, if you're, sometimes you don't have to balance the equation. Sometimes all you need to know is how many electrons are transferred. Now, I take that back. You do need to balance the equation. Right? And that'll become obvious once we get further down the line here. So if we split these out, the oxidation step is what? Well, if you go from a minus to a 0, you lost an electron. Right? So this one to this one, you lose 1 electron per bromine. Now this time I'm going to break with tradition, and I'm going to do the electrons while they're fresh. So if we lose 1 electron here, well, we do need to balance the, okay, I correct myself. You got to balance these first, then you can do electrons. So if we lost 2 electrons, they show up on that side. 1 electron each. 2 times 1 is 2. That hasn't changed. And then we have manganate yielding manganese 2 plus. So this one's going to go from a plus 7 to a 2 plus, which is what? It gained 5 electrons. We only got 1 manganese, so I didn't have to worry about that. Okay. Now, you don't have any oxygens up here, so there's no water and hydrogen steps for that one. But down here you do have 4 oxygens. Okay, that means you need 8 hydrogens. Okay, so let's see. Just checking myself. Yeah, okay, we're good. Now we need to balance electrons. We got 5 here and 2 there. So what do you do when you can't multiply one of the equations by a number and get the same value as you have in the other reaction? You got to multiply them both by different factors. And in this case, we've got an even there and an odd there. You got to cross multiply. So this one you multiply by 5, and this one you multiply by 2. So this is going to be 10. This will be 5. This will be 10. That one will be 16, 2, 10, and 2, and 8. There. Now we can add them together. Right? Electrons cancel. And now we have, let's do the manganese first. 2 manganate ions, and then 10 bromide ions, plus 16 hydrogens. That's it for this side. 2, 3. 1, 2, 3. And then this side we have 2 manganese, 2 plus, and 5 bromine liquid. And then we have 8 waters. Okay? Now let's see. Can we reduce it any further? Well, it's even. Uh-oh. Odd number. Even. We're stuck. That's it. That's what it looked like. Now, we could do the same thing with this one if we wanted to convert this to basic solution. You just neutralize these right here with hydroxyls, put hydroxyls on both sides, and then cancel waters. Now, that's something of a mathematical exercise, so anything's allowed. Then you have to wonder, well, is this reaction going to go in basic solution? Maybe it won't, right? Just because you write it that way doesn't mean it's going to be that way. But then you have to do some other ciphering to determine if it's going to go. And we've already covered equilibrium and entropy. So we could do some calculations and find out if this is even possible. I mean, is it thermodynamically favored? But that's another topic. We're talking pure electrochemistry now. Okay, this is my fake acid method, and these are the steps. You just use the half reaction method to give you the acid balanced equation, and then you cancel the hydrogens with hydroxyls. Hydroxyls, and don't forget, hydroxyls on both sides. Right? If you add something on one side, it's got to go on the other. And there it is. See, before we had this purple, and now I've added these green steps down here. Actually, it came straight out of your book, so I can't say I did it. and that'll balance your equations for either the acid or the base, whichever is required. All right, so why don't we balance the equations? I mean, just go straight to base. I mean, if you're going to balance the oxygens, just put hydroxyls on the other side. Balance those. Well, then what do you do on the side you came from? Well, you can't put hydrogen ions because that kind of defeats the purpose, right? So I assume that on the opposite side, you'd have to put water. I haven't tried it, but it probably would work. But why complicate things when we have a method that works, right? If you want to in your spare time, try to balance it first. Just skip the acid part and go straight to base. And balance OHs for your oxygens, and then balance the hydrogens using water on the other side. See what happens. I bet it'll work. All right. I don't want to sound like an equation balancing bigot. You know. Whatever works. Okay. So let me see. Here's another one. There's supposed to be an arrow in there. Oh, there it is. So if we balance this one in basic solution, you know what I'm going to do? I'm going to try to balance this one straight to basic to see if it works. Okay? So a lot of the steps are the same, so we're not actually wasting our time. So if this is our beginning position, manganate. Let's see. Oh, we better keep these because we've got a solid in there. And CNO minus and MnO2. Solid. Okay. This could give somebody trouble without some past experience and guidance as to how you determine oxidation states when you have, we can take oxygen as -2, but what do you do with nitrogen? Well, let's do the ones we know easy first. So this one is, what did we say that one was? 7, I think. Let's do it again. -8, -8. Yeah, +7. Okay. And this one is +4. Okay. So now we can go to the cyanide ion and the, I don't even know what that's called. So the rule is, since oxidation states, determining oxidation states is a method of bookkeeping for electrons. So we're not actually saying that we have ions in here, because these are obviously covalent compounds, right? They're all nonmetals, right? So they have to be covalent. But this method, this oxidation state idea, is used just to keep track of electrons. So we can sort of make up the rules as long as we're consistent, and the more electronegative gets the negative oxidation states. So in this case, oxygen is going to be -2. Nitrogen is 1 to the left of oxygen, which makes it -3. Right? So then we have -3 -2 is -5. Hold 1 out. That makes this carbon +4. Okay? And we'll do the same thing for cyanide. So that nitrogen is going to be -3, but we got to hold those 1 minus out for that charge. That means this carbon is +2. Okay? So now we can split the reactions. All right, there's a +2 to +4. That's the oxidized one. Let's see, let me make some more room up here. So the oxidation step is this one. Yields this one. Okay, the reduction step is the manganese. Plus 7. O4 minus aqueous yields MnO2 solid. And that's plus 4. Okay? Now, let's see. We've got to balance these. One manganese, one carbon, nitrogen, nitrogen. So everything but oxygen and hydrogen, hydrogens, not necessarily the protons, but O and H are balanced. Everything except O and H are balanced. So now let's see if we can do this straight basic. I'm not saying it's going to work because I've never done it before, but I'm willing to give it a try. So if we balance that O with an OH, it's got to go on this side, correct? All right. So now we got one hydrogen. So how we balance the hydrogens? It's not going to work, right? Because you make water on that side, you're just adding more oxygens. Okay, so I answered my question. Won't work. Not easily, anyway. All right, so we got to go back to our old method, the fake acid method. All right, so oxygen's here. We need water here. Right? That means we need 2 hydrogens on that side. And on this one, we got 4 here and 2 there. So we only need 2 extra oxygens on that side. Right? That means 4 hydrogens. There we go. Now we can do our electrons. All right, this one was plus 4. So this one's going to subtract or lose 2 electrons to make it go from plus 2 to plus 4. So those electrons are going to show over here. Right? Only 1 carbon, so 2 electrons per carbon means 2 electrons. On this side, we've got, let me make a little more room here. We're going to add, to go from plus 7 to plus 4, we add 3 electrons for each manganese. And there's only 1 manganese. There we go. So now we can reconcile. There's 3 here and 2 there. Cross multiply. There's a 2 there and a 3 up here. Okay. So we have a 3 here. We have a 3 here, 3 there, 6 there, and 6 there. Okay, we use that one up. This is an 8. This is a 2. Here's a 6. This is a 2, and that's a 4. Okay, use that one up. All right, electrons cancel. Let's cancel some other stuff before we bring it down. I need a fresh marker. Okay, notice on this side, we've got 3 waters. Got any waters? Yeah, we got 4 over there. So these waters cancel and leave us with just 1 water. So I'm going to put that down here so I don't forget. There's our 1 water. How about hydrogens? We got 8 hydrogens over here and 6 over there. So that means we're left with 2. So I'm going to put 2 hydrogens here. All right. Now I can bring the rest of it down. MnO4, 3 cyanides. So 1, 2, 3. That's it. Then we've got 2 MnO2s plus 3 CnO minus plus 1 water. So there, yeah, 3, there we go. So this is the acid version. Oops. It didn't go through all the steps. Okay, so now we got to get rid of the hydrogens. Right here. So we have 2 hydroxyls. Right? That makes 2 waters. And then we have 2 hydroxyls on this side. Okay? But we got 1 water over there and 2 over here. So we need 1 water left here. Get rid of that water. And that should be it. Let's see. 3CN minus, 2MnO4 minus, oops, and 1 water. Now on this side, 3CNO minus, 2MnO2, 2 hydroxyls. There we go. We're balanced. Okay. Before we go to the talk about batteries, you may on occasion be presented with having to determine the oxidation numbers for carbons in an organic compound. So I'm going to show you how to do that. It's not in the slides, but it just occurred to me that it might be valuable at some point in the future. And it's not something that my college instructors bothered with. I had to learn this the hard way. Okay, let me think if I can invent an organic compound. Remember, by definition, organic compounds are carbon and hydrogen, minimum. And then anything else, like oxygens, sulfurs. You can even have chlorines and other halogens and stuff in them. But they always have to have carbon, hydrogen, like methane, CH4, is an organic compound. But carbon dioxide is not. It has no hydrogen. So let's hook some carbons together and add some things to them. So let's say we have this carbon to that carbon, and we have another carbon here, and this one's got an oxygen, and then we got another one here, and there's a nitrogen. Okay? Now, everything else is going to be filled in with hydrogens, except for, just a second, how about this one? Put a chlorine there. This is a hydrogen, 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 and that's good. Okay, we're going to determine the oxidation numbers for each of these carbons. Notice, I'll just point out, each of these carbons has 4 bonds. That's just the way organic molecules work. They prefer, that's not always the case, but they prefer 4 bonds. So this one has 3 here and 1 there. 1, 2, 1, 1, 1, 2, 2, 1, 1, 1. Oops. It's a good thing I mentioned that. Got too many hydrogens. 1, 2, 3, 4. Okay, now it's kosher. Yeah. Okay, so when you're determining the oxidation number for carbon in this situation, you focus, laser focus on each carbon individually. If the carbon is attached to another carbon, there's no change in its oxidation number. Right. So this one contributes nothing to that. You look at these 2 hydrogens. This is +1, this is +1. This carbon has to be -2. Okay? Doesn't have to balance carbon. This carbon is attached to 2 over here. Right? So we only have to pay attention to this -1. So this carbon is +1. And this one is carbon, carbon, oxygen. -2. That one is +2. To balance. And then there's a carbon, but this one's attached to nitrogen. And remember, the more electronegative gets the negative. So nitrogen is -3. that makes this one +3. So we've got, let's see, +1, +2, +3, -2. In that single molecule, we've got 4 different oxidation states for carbon. Now, you may ask yourself, why does it matter? Well, during a chemical reaction, each of these carbons will act differently. And if you're trying to design a reaction to get a product, you need to know where the electrons want to go. Right? If you're designing a reaction that requires this molecule to be reduced in some fashion, you need to know that it has the capacity. Like this one could accept 3 electrons just to get to 0, and then it could go 4 more. The range for carbon is -4 to +4. It has an enormous range in oxidation states. 8 units difference. So they take care of that, and we'll move on to batteries. The galvanic cell. Now we're going to start to get quantitative with how we treat oxidation reduction reactions. A galvanic cell is a way of getting at those mobile electrons. When we were writing these balanced equations before, the balanced equation showed no electrons. Everything was happening underneath, right? And if you put those reactants in the same vessel and just let them go, the electrons will still move, but you won't have access to them. They'll move from one to the other, give you products. That's the end of it. It's wasted energy. So the galvanic cell is a way of getting at those moving electrons. In other words, you give those electrons an exterior travel route, so that if you can get the electrons out in a wire as they're going from one half reaction to the other, then you can put something in the middle and get some work out of it, like a flashlight or electric train or something. And that's the galvanic cell, a battery. Sometimes it's also called an electrochemical cell. Now, one other characteristic of the galvanic cell is the reaction must be spontaneous. In other words, the electrons move in such a way that thermodynamics say the reaction is spontaneous. It'll go from this side to that side with no intervention. You just have to put them together and it goes. Another characteristic is when you physically split half reactions, right? So you'll have one half reaction here and one half reaction there. This would be the oxidation side and this would be the reduction side, right? And you'll have an electrode here in the solution, an electrode here in the solution, and we might have a meter in here somewhere to measure it. Well, if this is the oxidation side, then which way are the electrons going? They're leaving, right? If it's oxidizing, those electrons are leaving. They're headed that way. And this is the reduction side. They're coming in here. So the oxidation and reduction reactions that actually take place in these half cells occur at the electrodes, because that's where the electrons arrive or leave. Okay? Now, sometimes the electrodes are reactants or products. Sometimes they're not. And I'll explain that in a minute. But there's one other thing here that I forgot to do. Anybody who's had physics knows that you cannot measure a current in a conductor unless there's a circuit. It's got to be complete all the way around. So, in this method, we use a bridge, and we allow ions to move. Right? If you don't allow the ions to move, then you're in the realm of electrostatics. Right? You build up an electrostatic charge on one side or the other. Now, it's not likely to occur, but I guess it's theoretically possible. But if you provide this salt bridge, then you have a complete circuit. Right? And that's the way electricity works. It works on circuits. So you might be wondering, well, I got a house and there's a hot wire coming in from the street off the pole. All right, that's only one leg. I mean, where does it go? I run it through my washing machine and it comes in one wire and goes out the other. Where's the exit wire go to? Well, if this is your house, right, and here's your power pole, and you got a line coming in, right? It's at 120 volts. Then what the power companies do is they say, why should we spend all this money on outgoing lines when there's no money in it? I mean, we can't extract any payment. We can only get money coming in, right? So they just use the earth as the return circuit. So once it's finished in here at your washing machine, it goes out to ground, and that makes the circuit. That's why sometimes they call it earth ground. And electricians will also refer to common wires. The common is the return wire at any particular device that goes back and all the commons meet at some place, and then they go into ground. Okay, so that was probably a little more information that you wanted. But since I have a captive audience, I thought I'd tell you anyway. So there's your galvanic cell. It has to be split into two separate half reactions. Now, we know what those half reactions are because we've done the balancing routine. I showed you a situation where we had a salt bridge. That's one way to do it, to complete the circuit. The other is just to put a porous disc in between them, right? Allows ions to flow freely from one side to the other to balance charge and to complete the electrical circuit. It works fine. In fact, this works better than the salt bridge. In every battery, I should say, there's something called internal resistance. Every battery resists the flow of electrons. It's just built in. And if you can reduce the resistance to that flow, that means you get a higher voltage. Now, what we've been calculating up to this point, and we're going to add in just a minute, is we can determine what is the maximum voltage that you can get from an electrochemical reaction. You'll get less than that because of various things like internal resistance. And this salt bridge has relatively high internal resistance. But the porous disc has much, much less internal resistance. So you're going to get a higher voltage out of that. And that all goes back to Ohm's law. If I can remember how to write it. Let's see. Equals I R. So you've all seen the triangle. Maybe you've seen the triangle. I don't know. Let's see. I, R, and V. So if voltage is up here, I is current, that is amperage, how many electrons are flowing per second, and R is resistance, then if you want to find R, you divide V by I, by the current. If you want to find V, you multiply I by R. If you want to find I, you divide V by R. That's an old electrician's trick. But if we increase this one, then we decrease the flow of electrons, as long as the voltage is constant. But if the flow of electrons has to be constant and the resistance increases, then the voltage, actually the voltage has to go down. But be that as it may, These galvanic cells are ways of extracting energy from the moving electrons. We just give them an external circuit. Now we have access to them. I've already talked about this extensively, so we're going to skip this slide. All right, more terminology, right? Just what you wanted. And you really just have to memorize it. If we put, if we use the standard arrangement and put the oxidation half reaction on the left and the reduction half reaction on the right, then the right, where the reduction takes place, is called the cathode. And the one where oxidation takes place is called the anode. Okay, you can just basically memorize it. But I rationalize it this way. The cathode is the side where cations are attracted. So we got these extra electrons flowing out into the solution. Negative attracts positive, right? So those exiting electrons are going to attract positive charges. They may not actually do that, but that's my logic. It's how I know how I can tell the difference between cathode and anode. Otherwise, just memorize the definition. And I've got yeah, we're close. I've got a little video coming up, so you get ready to turn your volume up so you can hear it all right. But some more definitions before we get to that. Cell potential. What is cell potential? Potential refers to voltage. That is, how much push is there behind the electrons. You think of voltage as a force. In fact, it's often referred to as electromotive force, EMF. But the unit of measure is the volt. Cell potential, sometimes it's got this fancy curly QE. That's a little hard to come by. I don't know how I got this one in here, but it's not something that you'd want to have to type a research paper with all that unless you had special keys set up. Quick keys. Sometimes it's just a capital E. All right, so what is this? If this is an electrical potential, what does it actually mean? Right? Volt, because the volt is not an SI. It's a derived unit. It's not a basic unit from the SI system. So what is it derived from? Well, the volt is equal to the amount of work that can be performed by 1 coulomb of charge. So it's work per charge. And this unit will be in joules, and this will be in coulombs, which is a measure of charge. So that's 1 volt. 1 volt is 1 joule per coulomb. In case you have to do any dimensional analysis, you need to know that. All right. Let's see, how am I doing on time? All right, we're good. All right, so here's your video, and I'm going to try to stay quiet because it picks up my microphone and messes with it. So I'm not going to say anything while this thing is running.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay. This is the galvanic cell that we would, if we were face-to-face in the lab environment, we would make this one. So how would we, if we wanted to measure the initial voltage for fresh cells, how would you do it? Well, you set it up, right, even with a salt bridge in there, but you leave this one side or the other disconnected. As long as you don't have a circuit, then there's no way for the electrons to get from one side to the other, and you will not have a functioning cell. When you get ready to go, say you want to time it for some reason, then you connect them, and you're off to the races. The other thing that the author, or the narrator, got wrong was that the cell doesn't stop working when zinc or copper is depleted. It stops working when the overall reaction has reached equilibrium. You need to know an equilibrium constant, and you can calculate at what point, what ratio, one side to the other, that will occur, right? When Q becomes K. So that was one mistake that was made in that presentation. Otherwise, it was okay, I thought. All right. So now, how do you measure cell potential? Right. There are two ways. One is called the voltmeter. It measures the voltage traveling through your meter, and in order to do that, you have to have current. In other words, you have to have electrons moving. So as the electrons are moving, you use Ohm's law. Use Ohm's law to determine the voltage. Well, how do you do that? Well, you have a standard resistance in your meter, and you run current through it, and you measure the current as it goes through the resistor. And then you use that formula, and the meter spits out this voltage value. That's cheap. It's very cheap, inexpensive. You can buy a multimeter for like $5 or less. Student models are even cheaper. So that's its main draw. The problem is, if you're trying to find out the maximum voltage obtainable from this cell, you don't want any electrons to move. Why? Because as long as they're moving, they're subject to that internal resistance. Not just built into the meter, but built into your galvanic cell. So you're getting a lower voltage than you could possibly expect. And remember, if voltage equals joules per Coulomb, remember the maximum amount of work you can get from a thermodynamic process is equal to delta G. What's the negative delta G? So in order to determine that maximum amount, you can't have current flowing through that cell because that's not a reversible process. It only goes one way, right? And the maximum of work only comes from processes that are reversible. That means they're either stationary or just infinitesimally moving one way or the other, so they can go backwards and forwards. That's where calculus comes in. So we're not going to dwell on that right now. So there is a way to do it, though. It's more expensive. It's called a potentiometer. Potential referring to electromotive force and electrical potential. So what you do is you set up this meter in the circuit. You got a circuit coming in here, and you got your meter, right, with a dial on it or digital output. And then you got the voltage. Say we're moving electrons from left to right. So that's the way they want to move. Once you've connected the cell, then there's a force being applied to move those electrons. So what you do is you apply this voltage from the cell. You apply an opposite voltage in the meter to oppose it. So this one's going that way, this one's going that way, and when they're equal, then no electrons are moving. But you have a measurement of the voltage that you're opposing. So the potentiometer gives you the maximum voltage obtained from that cell, which is translatable into available work. How much work can this cell do? Okay, but like I said, it's more expensive. You have to have a very finely calibrated device for delivering exactly the right voltage. All right, so this is probably a multimeter, the cheap version. And it'll do a lot of things. Now, multimeters with electronics, you can do numerous things. You can measure the resistance across a part of a circuit. You can always measure the current. All you have to do is put the meter in between. So the current has to flow through the meter. Voltage you can measure externally. And most of them are digital now. I guess some old timers like the analog dials, but I've sort of gotten away from those too. The only analog dial I like in my life is my wristwatch. It's easier to tell in just glance. I know what time it is. I don't have to sit there and read the digits. Okay. So that cell that was that galvanic cell that was in the video was a zinc copper cell. So one side, the zinc side, was the oxidation side, the anode, and the cathode was the copper side. But suppose you want to imagine a galvanic cell with other materials, like instead of copper, we want to put silver in there. What do you do? Right? Do you have to set it up and actually measure it? Well, we're going to follow in the footsteps of Hess when we were doing thermochemistry and adding reactions together to find out what the enthalpy of the reaction was before we actually did the experiment, ostensibly to keep from blowing ourselves up. So we have a way that we can calculate expected voltages for combinations of half cells. We call them the standard reduction potentials. Right? So they have this E, capital E, rather than that fancy script, E to the 0. That means the conditions in the cells have to be standardized. That is, any solutes in there are 1 molar concentration. Any gases that are introduced as part of reactants, and that's possible, have to be 1 atmosphere. And then the temperature has to be 25 degrees Celsius. I left that one out. all half reactions in the tables that contain this information are written as reductions, right? Standard reduction potentials, okay? And they range from high positive to very, very low negatives. So how do you make sense of that, right? Because one of them has got to be a reduction and the other one's got to be an oxidation. But if they're both written as reductions, what do you do? Well, first of all, you need some agreed upon standard, right? You can't measure the voltage of any half cell independent of another half cell to which you're connected. So we had to decide, you know, what should we reference all of our reduction potentials to? And it was agreed upon that we would use the standard hydrogen electrode, right? So you got one cell, and now depending on what the hydrogen electrode is connected to, it could be the anode or it could be the cathode. Okay, so I'm just going to write it one way here, but recognize that it could be the other way, depending on the other half cell. So the standard hydrogen electrode has water, right? And it has protons in solution, so it's an acidic solution. And then you have this pipe coming in right here, and your hydrogen gas source at 1 atmosphere. And this will be 1 molar. 1 molar hydrogen. So it's pretty concentrated. And then you have an electrode here. And that electrode goes out and it's connected to the other cell. Okay, so you've got bubbles coming out here, right? And the reaction is taking place at the electrode. Now, the electrode is not part of the reaction. It's not like the copper and zinc electrodes that were depleted or added to. This is like just a piece of platinum. It's a place for electrons to gravitate or be delivered for them to move. The reaction is the hydrogen and this one. Okay, depending on which way the reaction runs, is anode or cathode, it'll go one way or the other. Okay, so that's your standard, and that the voltage for this cell, this half cell, is arbitrarily assigned at 0. Now, if everything is compared to this 0, then you can compare the rest of them to each other. It really doesn't matter whether this is actually 0 or not, and I don't think it is. I read somewhere that was like maybe 4 volts, but you couldn't tell that because what are you going to reference it to? So once you have this list of voltages based upon this common half cell, the hydrogen electrode, then you can compare each one. Because if you set it up like this and then you set another one up like that, well, this side's the same, so those two can be compared. All right, so standard conditions. Also, here I answer the question. If they're all reduction potentials, how do you get a galvanic cell out of that? Well, one of them has to be flipped. You got to reverse it. And what do you do with the voltage that's listed in the table? You just change the sign. If you reverse a reaction to oxidation, then you change it from negative to positive or positive to negative, whatever the case may be. And then you have your half cells with voltages, right? Once they've been written correctly, oxidation, reduction, then you can add them together, and that's the voltage for your cell. Now, when will it run spontaneously? Well, I'm going to prove it to you in a minute, but for now, the voltage, if the voltage is positive, you've set it up correctly for spontaneous reaction. All right, this came straight out of your book. This table, I had to split it right in half here. So this one's going to go from fluorine to fluoride. Referenced against the standard hydrogen electrode is 2.87 volts. Right? So that's definitely spontaneous. If it's with a hydrogen electrode, it would be plus 2.87. That's spontaneous. So it's going to go that direction. And then it just, notice they're in order, right? The highest voltage, it goes on down here. And then we have to skip to the next one. It goes, there's 121, it goes down 0.52. And then back up here, it goes 0.444 down here to the hydrogen electrode, right there. And then anything past this, below it, starts to get more and more negative. So as written here, against the hydrogen electrode, that would not be spontaneous. Right? So in this case, we would make this one, flip this one for the anode, make that positive, and then against the hydrogen electrode, the voltage would be 0.036 volts. All right, so this table is in your book. It's also in useful information in the review documents, and it should be in review documents, useful information in the folders where you find your exam. Okay, so this is the way I was taught. And if it works for you, great. So I'll do this one first. Notice that when you're going to find the potential of your cell, you take the cathode as is, right? Because it's written as a reduction. And then you subtract the voltage for the anode, because that's negative converts the reduction potential to oxidation potential. Then you can add them together. But in order to do this, you've got to identify which one's the cathode and which one's the anode. Right? So that's the first step. Once you've identified which one is on the reduction side, which one's on the oxidation side, then you can run this formula. If you don't know that, then you can't use the formula. Okay? Oh, before we leave this slide, if we have to multiply a half reaction by some constant value, like we did before, to make the electrons balance, what does that do to the standard reduction potential? Absolutely nothing. The standard potential under these conditions is an intensity property. Doesn't matter how much you have. So the potential, the standard potential, doesn't change. Now, that doesn't mean that the cell, if you mix the cell up in non-standard conditions, you will get a different voltage. Well, we're going to deal with that by another route. Okay. So here's an example. You got these half reactions. There's iron being reduced to iron 2 plus, copper 2 plus to copper. And here are the reduction potentials, 0.77 and 0.34. All right. Which one's the anode and which one's the cathode? Well, if we look at it this way, iron is being reduced. So it's the cathode, right? Going from 3 to 2 plus. And this one is going from 0 to 2 plus, which means it's oxidized. That means this one is the anode and this one is the cathode. So we would say 0.77 minus 0.34 would give us 0.43 volts, 0.43 volts. Now, how many electrons are transferred? You got to do some balancing there to find out. In this case, 2 electrons were transferred in the stoichiometric equation, in the balanced equation. All right. Now, how do I do it? My method is I look at the numbers, right? I say, all right, if I change the top one to negative, add them together, that gives me a negative. That's not spontaneous. But if I change the bottom one, change the sign on the bottom one and add them together, I get a positive. So that's the one I changed. This is now the anode. I know it's the anode because of the effect of sign change. So that's the way I do it. You can do either way. You end up in the same place. Okay, so we already talked about that. Okay. If the standard potential doesn't change when the equation is multiplied by a constant value, why should we even care about the balanced reaction? Well, here we go. If we want to create a galvanic cell under non-standard conditions, which is most of the time, we need to know how to calculate the actual voltage for that cell. It won't be E0 because the voltage depends upon the equilibrium situation for the overall reaction. So that's why we need to know both the concentrations of reactants on both sides in each half cell, and we need to know how many electrons are being transferred if we're going to do the calculation. And we use an equation proposed by, man's name is Nernst. What was his first name? Walter Hermann Nernst. He was a German, of course. He'd have to be for a name like that. But the Nernst equation is it's like, I don't know, it's like Newton's laws of physics. It's that central to chemistry. And in order to use Nernst equation, we need to know balanced equation and how many electrons are moving. Okay. I'm going to insert something here and give you whiplash. Hold on a second. Yeah, okay. We'll come to the Nernst equation in just a few minutes, so hold that thought. Let's see if I can dispense with these two slides quickly. I'm tempted to cut them out of the discussion altogether. But if we're looking at oxidizing agents, right? Remember, an oxidizing agent does what? Is reduced. Because an oxidizing agent is responsible for the oxidation of the other reactant. So it has to be reduced. So if we're looking for the strongest oxidizing agent, we want the one with the greatest reduction potential, the largest positive reduction potential, right? So we can look that up in the table if there is a value in there for any one of these species. Well, let's look at it this way. Which one of these are even going to be available for reduction? Right. Well, first of all, if we wrote them, if we look at, let's see, iron metal, sodium metal, fluoride ion, sodium ion, chlorine, there are no values in the chart for sodium, fluorine, and iron. And you say, well, yeah, there are. Well, not for reduction. If you write them backwards, then they're not reduction anymore. So if we take fluorine gas and reduce it, there is a voltage there, right? We saw that one at the top of the table, right? Okay, got that one. That's good. Okay, how about sodium? Well, we look at sodium. It's a minus 2.71, right? Sodium ion, that was one of them, right? How about sodium metal? What would that look like? Oh, my mistake. This is for a reduction of fluorine gas. This is not for a reduction of the fluoride ion. Right? Fluoride ion will not reduce. It's already got an electron. It doesn't want any more electrons. So that's really a moot point. I mean, it's non-existent. Sodium ion, right? Okay, sodium ion's there, right? What about sodium metal? If you try to add an electron to sodium metal, it doesn't want it, right? Metals want to give up electrons. So that one doesn't have a value either. Chloride's got a value. That's okay. We can go with that. And how about iron? Right, there's your iron. And we try to reduce iron. It's the same as sodium. It's a metal. It doesn't want electrons. So what do we do? Well, let me see. Let me look at my hard copy. I went too far. Hold on a second. Okay. Little animation here. Sodium can't be reduced. These with the question marks, they go on the far right side. I mean, they're not oxidizing agents to begin with. But chlorine is a relatively high value, 1.36 volts, right? And sodium is lesser so. Sodium ion, that is. So the sodium ion and the chlorine, we can make a judgment there because they actually have reduction potentials. But iron, metal, sodium metal, fluoride ion, they don't have reduction potentials because they don't want it. I mean, they're not going to be reduced in a spontaneous process. Now, if you force the reaction in reverse, it's possible. Anyway, so now really the only order we've got is between chlorine gas and sodium ions. And the chlorine gas is going to be the stronger oxidizing agent. That answers the question, actually. It's most easily reduced. It's the strongest agent. All right. So I wasted enough time on that one. Let's look at line notation. It'd be kind of a bother if we wanted to describe a galvanic cell to have to draw the beakers and the salt bridge and all that garbage, which is useful from time, you know, for laboratory purposes. But it's not very good for publishing. In other words, publishers like to have easy stuff that they can typeset. And graphics and pictures are more expensive to publish. And plus, when your mind is moving, you want something quick that you can write your thoughts down quick. And line notation for the galvanic cell is just that. So there's some rules that are required to write line notation and describe your electrochemical cell. The anode is always on the left when you write the elements and the ions and so forth in order. Anode starts on the left. Cathode is on the right. Well, what separates them? Right? What separates them is a porous disk or a salt bridge. Right? So you separate them with a double line. Right? That's your salt bridge. So on the left-hand side, you're going to have the anode. All right? So you write them in order of the reaction. Right? So for the anode, you're going to have something here, and it's going to be oxidized to something here. If there are any phase changes involved, then you separate them by a single vertical line. If they're all mixed in the same solution, then you just use a comma. I didn't put that in there, but that's, you'll see that. If you have the concentrations, it's a good idea to write them in somehow, maybe in parentheses or underneath, because that's important information. Here's an example. So the anode on this side oxidizes magnesium metal to magnesium 2+ ions. And they're different phases. Notice solid, aqueous. So you have a vertical line between the two. Then you have your salt bridge, or your porous disk. And then on the cathode side, we're reducing aluminum 3+ in aqueous solution to aluminum metal. And there's the phase change difference there. So that is a simple version of line notation for our galvanic cell. More explanation. So I mentioned earlier, I just want to make that point, drive it home. There are some chemical reactions that occur only in solution. So your half reaction is right there in the solution, and the electrode doesn't participate. The electrode is there simply to transmit electrons. It'll either accept them and send them into the circuit, or they'll come through the circuit and out that electrode. So what you need is some way to get those electrons into that solution. On the research level, lots of times we use platinum electrodes because platinum is inert. It won't react with anything. At least not anything that we're going to be using in the lab. But on industrial scale, we can't afford platinum. Besides, with many of the electrochemical reactions that occur in industrial settings, the environment is too aggressive. It will actually erode platinum. And once your platinum's gone, I mean, that's a couple of $1,000, $3,000, $5,000 down the drain or more. So you need something else that's cheap. And graphite rod works great. Graphite is dirt cheap. So you just use that as a conductor. Okay, so if we want to describe this cell where we've got iron and silver, iron 3+ to 2+, and silver +1 to silver metal, we want to know which way is it going. Well, if we use my methods, if you make the first one the anode, you get a negative summation. So that's not it. The second one has to be the anode. We've got to reverse it to iron 2+ yields iron 3+ plus electron. That makes this negative, and the difference is 0.03 volts. Here we go. Cathode, anode. And that's the way you would write the reaction. And we can see from the half reactions that we only transferred one electron for the balanced equation. Let's see. All right, you already know that stuff. Are we going to do line notation? Maybe not. Okay, we're not going to do. Why don't we do line notation? Let's just take the reaction. So we'd write it like this. We'd have right, anode on the left. So that means iron 2+ to 3+. Iron 2+ and iron 3+. And they're aqueous. Aqueous. But they're both aqueous, right? So we don't have a phase difference. We just put a comma there. And on the other side, we have silver being reduced to silver ion being reduced to silver metal. So silver ion to silver metal. There you go. So that's your line notation for this cell. without concentrations because we're doing it at under standard conditions. And that's the assumption. If you don't write concentrations in there, if you don't say the conditions, we have to assume that the conditions are standard. Okay, let's see. So there's our cell with the cathode on the right with silver and iron, and this is a platinum electrode. So what's going to happen over here? Well, you're just going to go from 2+ to 3+ iron. That's it. And the electrons that you generate go up through the wire and over to the other side. On this side, what's happening? Well, you're converting that to metal. So where's the metal end up? Well, at the reaction site on the electrode. So the electrode is going to pick up silver metal. Its mass will increase as the reaction proceeds. Right? So that begs the question, does this electrode really need to be silver? If you're getting silver from solution and it's depositing on the electrode, look, no, you don't have to have silver there. You only need silver there if you're going to run the reaction in reverse. And then you need to extract silver from the electrode, put it in solution. And that's running it backwards. We'll talk about that in a minute too. But theoretically, you could make both electrodes out of platinum and still run just fine. The key is what's happening at the electrode for these ions. Okay. And notice we've left out the spectator ions, right? All the, I don't know, chloride ions or sulfate ions or whatever the case may be. It wouldn't be sulfate because it wouldn't be chloride. Silver chloride would precipitate out. Nitrate would be good. So if you use nitrate for both sides, then you would have balanced anions involved. Oh, I'm sorry, I left out the platinum. All right. My mistake. Now, this is a description of the galvanic cell. That doesn't say that the platinum is intimately involved in the reaction, but it is a component. It's actually in that cell. Its only purpose is to conduct electrons. So there's your phase change also. Okay, so this is sort of a pulling everything together. You have to decide which is the anode, which is the cathode, calculate the standard potential, balance the reactions, and keep track of your electrons for later. So here's silver and copper together, anode on the left and cathode on the right, with the salt bridge. And what do they want us to do? Oh, just sketch the cell. What's the potential of the cell? Okay, here it is. Under standard conditions, it's 0.46 volts. Okay. So we have to look up the cathode here. The silver side is 0.8, and the anode, the copper side, is 0.34 positive. We make it negative, and that gives us a positive 0.46 volts. So it runs spontaneously from this side over to that side. Okay, now let's think of this galvanic cell in terms of equilibrium. If we were to, and we can do this just looking at the half cell, what would happen to the potential if you increase the copper ion concentration? So copper ions over here on this left side. You increase the copper ion concentration, notice the reaction that it's describing. This half reaction is copper is yielding copper 2+ ion plus the 2 electrons that go up the conductor. Well, Le Chatelier says if you increase the concentration here, you're going to drive the reaction, it's going to shift back toward copper, right? And that means fewer electrons running up that conductor. So the voltage will increase. There's not as big a push on the electrons if we increase the copper concentration in solution. Conversely, if you decrease this, it's going to favor the production of more electrons, and that will increase the voltage. Now, of course, there's a lower limit, I'm sure, because once you get to no copper ions, then the reaction won't go. But once you get down to very small levels of copper ions, now what happens is you reach equilibrium quicker. So there's a trade-off. We could do the same thing on the silver side. Just use the silver half reaction and do the same sort of logic. So let's draw some comparisons, parallels, relationships between work and cell potential. We'll go back to that original definition for voltage, right? This is the voltage, electrochemical potential, is work divided by charge, right? Now, why do we have that negative there? Well, we have that negative there because of our definition of system and surroundings, right? If you have a system here and it's doing work on the surroundings, that's a negative value because work is leaving the system. But if it's doing that and this reaction is spontaneous, then the voltage should be positive. For a spontaneous process, the voltage is positive. So how do we reconcile them? Well, we have to fudge. We just say, okay, the voltage is equal to negative W over Q. Right? And in that case, now, negative W equals Q times E. So we multiply the coulombs times the voltage, we get joules with the correct sign. And the maximum amount of work is charge transferred, negative charge transferred times the maximum voltage. And right, remember when we were measuring that voltage? The only way you can get the maximum voltage is with a potentiometer. A voltmeter won't give it to you. I mean, you can ballpark it. Right? You'll be less than maximum, though, if you use a voltmeter. But the potentiometer will give you the maximum voltage obtained from that galvanic cell. And then you should multiply it by the charge. And this charge has to be in units of coulombs. Right? That's a physical. Right? We're used to moles of electrons, right? In physics, they speak in terms of coulombs. And since they figured it out first, they get to call the shots. So what we have to do is learn how to convert moles of electrons to coulombs, and there is a conversion factor. Okay, well, that's more of what I was telling you earlier. Let's see. Charge transferred times the maximum volts. Charge transferred, right, times the maximum volts is the maximum work. Right, that's just added explanation. Okay. So, but this is not telling you anything new. In any spontaneous process, you always lose some energy. Right? There are inefficiencies in any energy transfer. We identified one as entropy, right? But there are others. So the actual work that you get from the galvanic cell is going to be less than the maximum. But it's instructive. It's information that's good to have. to know what's the maximum work that we can get. That's like our target. And we get up to a certain amount. Oh, we can't get past that amount. Okay. We'll get some young graduate student to set his mind to it. We can't be bothered anymore. Okay. So here's your conversion. It's called the Faraday. The Faraday is named after Michael Faraday, who was a genius at laboratory experimentation in physics. He could devise some experiments that were just, I mean, they were so simple. And there's a term in the sciences we use for simple reactions, simple mechanisms for experiments that are designed to give the maximum amount of information. They're called elegant. Elegant experiments. Well, his equipment was elegant. And he extracted bushels and bushels of information out of these simplest mechanisms. Okay, enough about that. 1 mole of electron is equal to 96,485 coulombs. Okay, that's in the useful information. 96,485 coulombs per mole of electrons. So 1 mole of electrons will give you 96,000 coulombs of charge, which is pretty high. So you don't want, and that's electrostatically speaking, right? If you had that, a mole of electrons gathered in one place, they would have this massive charge. And one place that you can get those is with a Van de Graaff generator. You've seen them. This tall tube and with a big silver ball on top, and you plug it in the wall and turn it on. It deposits charge on that ball and builds up a huge electrostatic charge. And if you hold a conductor in insulated gloves, of course, up there and ground it, you'll get a big spark, right? So, and the farther away you can get a spark, the bigger the charge. Anyway, that's our conversion factor for moles of electrons to coulombs. Now, why would we need to know that? Okay, we'll cover that in a little bit. Because of the definition of current, a measurement of charge per second. So current is given the symbol I, and it's equal to the amp. 1 amp is equal to 1 coulomb per second. That is, at a stationary observation point, if you can measure a coulomb of charge passing that point every second, that's 1 amp. And that's really high, actually. What do they say about electrocuting condemned prisoners? It's not the voltage that kills you, it's the amperage. How much charge goes through your body in a second. They use high voltage just to make sure it goes, right? You got to have a certain amount of push or it won't even move. Okay, so we'll come back to that in a minute. Work a problem, actually. Now, let's make the connection between voltage and free energy, right? We know that negative free energy means spontaneous reaction in thermodynamic terms. So how's that related? Well, we know that delta G is equal to work, right? Delta G is the maximum amount of work you can get from a process. And for a galvanic cell, we've already determined that maximum work is equal to minus charge times voltage, electrical potential. Well, if A is equal to B and B is equal to C, then A must be equal to C. So that's equal to that. And that is equal to that. That means this is also equal to that. Okay, so now that we have that equivalence established, we also know that the charge in coulombs is equal to the number of moles of electrons times the Faraday. That conversion factor right there, right? The number of moles of electrons multiplied by that leaves you with coulombs, right? So NF is a valid substitution for Q. And I didn't mention it earlier, but now we're using Q to talk about charge. In thermochemistry, we use Q to talk about heat. So I apologize for that. That's just, it's legacy. It's grandfathered in. Actually, the physicists did it to us. Right? Chemists think Q is heat. And physicists say electricians, glorified electricians are physicists. The Q is, for them, is charge. So if we substitute that in here, we get minus NF times E. Right? Right there. Oh, there's Michael Faraday in his younger days. Okay. So that means that these two terms are directly related, right? The free energy of the reaction related to the voltage of the reaction using these conversions, right? How many electrons transferred and the Faraday constant. Oops, sorry. So this also proves what I told you earlier. Remember, negative G is spontaneous. Positive E is spontaneous. So if this is positive, that's positive, then a negative times a positive yields a negative. So now we know that a positive voltage leads to spontaneous process. All right. Now here's another fly in the ointment, kink in the chain. We can set up two half cells using exactly the same half reactions. Now, of course, if they're both the same concentration, what's going to happen? Nothing, right? They're at equilibrium if that's the case. But if we make one of them lower concentration than the other, we get what's called a concentration cell. And in this case, the one with the lower concentration is the anode. Why? Because with lower concentration, the shift is toward more ions, right? If you look at it this way, like that, then if you decrease this concentration, you're going to shift it that way and produce more electrons. As opposed to the other side, where you're increasing this and you're shifting it that way. So on this side, the concentration, the higher concentration means that you're going to produce a cathodic reaction. On this side, the lower concentration means you're going to produce an anodic reaction. The only difference between the two is the concentration. That's why they call it a concentration cell. Okay. Now to Walter Hermann Nernst. This was a younger picture. But he was active at the end of the 19th, beginning of the 20th century in lots of different things. So he gave us the Nernst equation, which I'm going to show you in a minute. But he was also into thermodynamics, physical chemistry. Gives me shivers to think of that one. And other types of solid state physics. In fact, he proposed a heat theorem that was instrumental in formulating the third law of thermodynamics. And for that, he got the 1920 Nobel Prize in Chemistry. But this Nernst equation he came up with earlier in the 1987. So he was what? 23 years old, roughly. So he did this one when in his youth. And that's always been a rule of thumb. Really productive scientists do most of their good work when they're young and starving. It's the older ones that sort of sit back and dabble with things that they're never going to solve. And Einstein said it. People ask him, why are you trying to develop the grand unifying theorem for all physical laws? He says, I can afford to. This was in his old age. He says, I've already made a name for myself. I did that when I was young. Young scientists have to focus on stuff where they get results and make a name. My name's already made. I can afford to spend time on this, dabbling around on this insurmountable problem. Anyway, so what the Nernst equation does is it draws the relationship. It establishes mathematically the relationship between cell potential and concentrations of the components. So now, if we can change the concentration and calculate the potential, then we can set up any cell we want. We base it on the standard potential, but we set up the cell with any concentration we want, and we can calculate its expected voltage. Right? So there's the equation in its raw form. The actual voltage here, E, electromotive force, potential, is equal to the standard potential minus this term. Right? There's your gas constant, there's your temperature in Kelvin, there's your number of moles, right? That's why we have to keep track of the number of electrons. And there's your Faraday constant. And this is the natural log of Q. Now Q, big Q, capital Q, hasn't changed. It's the same meaning as always. That is the ratio using the balanced equation. Q uses the K law of mass action expression only with non-equilibrium concentrations. Remember that? So you calculate the Q, take the natural log, multiply it here, divide there, subtract that from standard potential, and that gives you the actual potential. Okay. That's kind of unwieldy. So we've sort of simplified it. We say, all right, what are most conditions in the laboratory? Right? They take 25 degrees. Yeah, okay, that's fine. So we could plug in 25, we could plug in here. And the Faraday's a constant. So we can take these three terms, R, T, and F, and combine them into one. Right? So there's the R, there's the temperature at standard conditions, and there's your Faraday constant. Put those all together, plus one more. We don't like natural logs, unless we have to. So this version converts the natural log to the common log. And in order to do that, we need this term, 2.3026. Now, if you combine that one, that one, that one, that one, you get 0.0591. And in the numerator, in the denominator, the moles of electrons that are transferred. And then you have the common log of Q. Now, you may be wondering, is he just pulling my leg? 2.3026 times that common log. You know, I can hear voices in the background saying, all right, prove it. Okay, here you go. I anticipated your question. This is a proof for that relationship. Natural log of Q equals 2.3026 times the log base 10 of Q. So, be that as it may, we'll go in and just use it, right? Oh, before we do that, all you need to do is to get your balanced equation, the concentrations that change, right? If there's a solid or a pure liquid, throw them out. They don't count, right? I know we had one reaction over here with manganese oxide, MnO2, was a solid. It would not be included in the Q expression because it's not part of the K either. But get the ones that go into the K and calculate them as a Q, and then determine the number of electrons that actually move in that reaction, then find the standard potential, and you can calculate E, the actual potential. Now, next thing I want to look at is the equilibrium situation. So, when our galvanic cell reaches equilibrium, what happens? No voltage, right? There's no incentive for the electrons to move anymore. They're all happy. Now, of course, we know kinetically it's right furious back and forth, but there's no measurable voltage. Let's put it that way. So E equals 0 for equilibrium condition, and Q equals K. Right? So under those conditions, this actual voltage here is equal to 0. What about E 0? It doesn't change because it's at standard conditions, right? It's not at equilibrium. This one's at equilibrium. That one's standard conditions, so it stays the same. But now this becomes 0, and the Q becomes K because we're at equilibrium. So notice what we can do. If we solve for E0, and we know E0 and the number of electrons that are transferred, we can calculate K for that reaction. All we need is the standard voltage and the moles of electrons that transfer. Or it's like any equation. We've got what? A value here, value there, and value there. If you know two of them, you can solve for the third one. And that's one way to get the equilibrium constant for a reaction. Okay, let's see. So let's say we have this reaction. So here's our reduction potentials. So how would we arrange that? Right? If we make this one negative, then that won't do. So we have to make the bottom one oxidative. That's the anode. So we reverse that one. And that gives us a total voltage of 0.67. Okay. Here we go. Here we go. 0.67 there. All right. We know E0. How many electrons are transferred? Well, let's see. 2 there, 2 there. 2 moles of electrons. Okay. We know E0. We know moles of electrons. We know it's at equilibrium. Or we're saying it's at equilibrium. Now we can calculate K. There you go. So log K is equal to this expression, and then K would be the anti-log of 22.6. So 10 to the 22.6 power is K. Oops, there it is right there. 4 times 10 to the 22nd. Sorry.
Thank you.
And that's not unusual for electrochemical reactions, redox reactions. They usually do have very large K values. So what does that mean? In reverse, the value would be very small. But that doesn't mean you can't run it in reverse, right? All you need to run a reaction in reverse is a voltage that exceeds the cell voltage in the opposite direction. It's like the potentiometer where we were balancing. Well, if you go too much voltage in the opposite direction, now you reverse the reaction in the anode and make it a cathode. We'll talk about that again in a minute. The difference between E and E0. When is E equal to 0? Equilibrium. Dead battery. Right? How about E0? When is E0 equal to 0? Think about it. E0 is equal to 0 for a concentration cell because you don't have two different half cells. You got the same half cell on both sides. So standard conditions say you're not going to get a reaction. E0 is 0. Those are two important factors to remember. Okay, so here's an example, this sample problem, and let me see. Yeah, I better get a move on. I think I can make it. We'll make it by 12 o'clock. But notice with this scenario, a concentration cell is constructed using nickel and nickel 2+. Right? So both anode and cathode have those. In the one of them is 1 molar and one of them is 10 to the minus 4th molar. So which is which? Which one's the cathode and which one's the anode? The high concentration is the cathode. The low concentration is the anode on the left-hand side. So in order to tell them apart, we say this one is the cathode reaction, this one's the anode reaction. Put them together, and how many electrons were transferred, right? We actually don't have to put them together to figure that out, right? 2 electrons here, 2 electrons here. So that N will equal 2 right here. And that's a constant. Well, yeah, it's a constant in these circumstances. What's Q? Well, Q, in order to do that, you need the balanced equation. Yes, that's true. The Q is the anode concentration divided by the cathode. So the lower concentration divided by the higher concentration. And take the log of that. So here it is, 10 to the minus 4th divided by 1. So the log of 10 to the minus 4 is what? Minus 4. And minus 4 times this and a minus gives you a positive, 0.118 volts. And on your meter, if we were in the lab, we would change the scale on our meter. Normally you say, okay, the meter it measures up to, I don't know, 200, 300 volts. You change the scale to millivolts. And 0. Well, that's not working. 0.118 volts is how many millivolts? Well, a millivolt is 1,000th of a volt, so it takes 1,000 times as many to equal that. So that's what you would read on your meter for a concentration cell. Generally speaking, the concentration cells produce voltages that are much less than any other combination of what we would consider standard galvanic cells. Concentration cells always produce low voltage. Now, how would you increase the voltage of that cell? Well, either increase the denominator or decrease the numerator. Remember when we talked about Le Chatelier? Decrease the ion concentration on the anode side and or increase the concentration on the cathode side. And that makes this ratio smaller, which means, now is that going to do what I want it to? Let me just do a calculation. Say we decrease the voltage from 10 to the minus 4th to 10 to the minus 5th. Just one order of magnitude. Okay, and then we'll take the log of that, and then we'll change the sign, multiply by 0.0591, and divide by 2. So now the voltage is 0.148. Do you have an appointment?
Excuse me, 2:30 this afternoon or 9 o'clock in the morning.
Okay, we should go this afternoon.
Okay.
Okay. So that's a concentration cell calculation. right, so where are we headed with this one? All right. This is just a practice problem. If you make a galvanic cell, 1/2 reaction is going to be nickel and nickel 2+, and the other side is going to be silver and silver plus. So which one's which? Well, my method says if the reduction potential is 0.8 here, and you make that one, if you flip that one for the anode, you get a negative number. So we need to flip this one. So the nickel electrode is the one that'll be written as an oxidation, the anode. So it'll be plus 0.23, and add them together, you get 1.03 volts. Right, there's your line notation, right? So we've decided that the nickel is the anode side, so we write it as an anode, right? This has to be oxidized to that. And then the cathode side is silver ions are reduced to silver metal. And there's a sketch, right? I use a drawing program to do this. I do that by hand. It used to be my master's degree, I had to draw my figures by hand because that was before computer-aided design. Okay, so that's what it would look like. We got a salt bridge here with sodium nitrate, right? Okay, so I picked right. Nitrate, we want nitrate here because if you put chlorides in there, you're going to precipitate out all your silver. That won't do. Okay, so here are the half reactions. There's your voltage. Oh, that's as far as they wanted us to go. Now we're going to look at some other types of galvanic cells. Batteries. This is before we talk about running the reaction in reverse. These are spontaneous reactions. This battery, everybody's got one under the hood of their car, unless you've got a what is that all-electric car? Elon Musk's car. I can't even remember what it's called. Anyway, probably because they're going to go out of business anyway.
Tesla.
Tesla, yeah. Without government subsidies, they wouldn't survive. It's kind of like the ethanol industry making ethanol for gasoline. Without subsidies, you couldn't afford to convert corn into ethanol. They'd go bankrupt in 6 months. Anyway, this particular battery has 2 half cells, obviously. One of them takes, well, here's more important. Both of them end up with the same product. They both end up with lead 2 sulfate. Okay, so if this is 2+, how do I know that? Because sulfate is 2-, so lead has to be 2+, right? So how do we get there? Well, let's see. In my tradition, I want oxidation on the top. So what we use is a plate of lead 4 oxide. Okay? And it produces that. But we also need sulfuric acid. And on this side, we have pure lead plate and sulfuric acid. Okay? So this one, the oxidation, oh, I wrote that wrong. This is oxidation. And this is reduction. My mistake. Because you're going from, no, I got it right the first time. 2+. Oh, that's right. Yeah, that's oxidation. We're losing 2 electrons here. and this is gaining 2 electrons. Okay. The nice thing about this reaction is you don't need a salt bridge. You don't need to separate the electrolyte, sulfuric acid. Why? Because it's common to both cells. You just need to keep the cells separate from one another so that the oxidation and reduction reactions can happen at the surface of the plate. And notice, as the reaction proceeds, you're producing this solid deposited on the plate. When you run the reaction in reverse, when you're charging your battery, the reactions go backwards, right? They're reconstituted. Now, with modern plate design in our batteries, you can do that hundreds and hundreds and hundreds of times without serious impact on the efficiency of your battery. But in olden days, and even today with really old batteries, you can get a condition is what's called sulfating out. You can coat those plates with so much lead-2 sulfate that now the reaction won't proceed. You can't, the acid won't penetrate. So you cannot get the reverse reaction to recharge the battery. And at that point, you just scrap it and let some specialist reclaim the materials. Okay, so that's not a complete half reaction. I don't have time to go in and balance the reactions, but my guess is it's probably there in your textbook too. Okay, another type of battery, the dry cell. Now the dry cell is typically what we see on the grocer's shelf. The C size, the D size, C size, AA's, AAA's. They left out B's. I wonder if there's a B size. D, C, skip B and go to, or an A size. I bet there is. They're just not popular. Anyway, the dry cell is a like an umbrella or a category of batteries. The chemistry that goes on there could be this manganese oxide and ammonium chloride, but there are tweaks to it. So the dry cell can be produced by various things, and it's called dry simply because it doesn't have a liquid in it. It's got really just a paste, but it's an electrolyte paste that allows ions to move. If they don't move, then you're stuck. There's nothing's going to happen. Okay, so this central carbon rod here is just a conductor, right? And if this is at the cathode, right, that surface right there is where the cathodic reaction takes place. That means electrons are coming into this rod and they're going right out the top. So the dimple on the top is the negative charge, is the negative pole for this battery. The anode is composed of this zinc case right here. And that zinc case is insulated from this carbon rod. It has to be, otherwise you get a short. And that's where the electrons enter. So the electrons go out the top, do their work, come in the bottom, and react with the zinc. Okay. So that's the dry cell. Now here's another type of dry cell. It's not used much anymore simply because it's got that mercury in it. But there are other types of small disc-like batteries, right? Used to be, people don't mess with them much anymore, but it used to be something that we do quite often with personal computers. If you had something mess up with your CMOS, your BIOS setup, you just go in and pull the battery out, because every board, even now, every motherboard has one of those little 5-volt batteries, those little silver thin discs. It's this type of design. And you have to have that trickle of electricity going through your system or it forgets where it was. Well, we take that battery out and it forgets where it was and it goes back to its original read-only memory, right, which doesn't need a battery. And then you put the battery back in and boot it up and it's back at its factory set conditions. There are other types. Hearing aids, they have these little tiny batteries like that one, only doesn't have mercury in it anymore. But it's a dry cell battery. I think they're made with silver. I think it's common there. Silver is the currency for hearing aid batteries now. The fuel cell. The holy grail of electric powered vehicles. Now, why would the fuel cell be so important? One reason is you're not stuck with a starting concentration of reactants at the cathode and anode, right? Anode over here, cathode over here. You're not stuck with a certain amount of reactants in either side, either half cell, because they're constantly being replenished. Right? It's still an electrochemical cell, but you're replacing used up components. And what you get as a product is steam, right? Water. So they're non-polluting. At least the battery's non-polluting, right? How do you produce the hydrogen? That's another question. It probably produces more pollutants than a coal-fired power plant, but that's another topic. But the fuel cell will run and run as long as you've got fuel going into it. The fuel cell was used extensively in NASA's, I think they started testing them on the Gemini, the two-man probes, two-man capsules, and then they were perfected and relied upon heavily for the Apollo missions. In fact, when the Apollo 13 was on its way to the moon and its oxygen tank blew up, it lost one stream. It lost that oxygen right there. So that was losing power because it used fuel cells, and it was losing breathable oxygen. So, and they also had built-in batteries too, but they would last only for so long. Their main power source was fuel cells. Well, it was a new technology, and those fuel cells, oh man, they ran hot. Not only couldn't you touch them, you couldn't get paper near them. So they had to be heavily insulated. Since then, the technology for fuel cells has improved to the point where they're still hot, but they're not nearly the scorching temperatures they used to be. The other problem with making a fuel cell as the power source for automobiles is how do you get the hydrogen in there? Right. There are other types of fuel cells. Let me put it that way. You can use methane as a fuel for a fuel cell, but it's still a gas, right? It has to be a gas to make it to cross the barrier. All right. So whether it's hydrogen or methane or whatever it happens to be, you still got to have an efficient way of storing enough reactant to take you 200, 300, 400 miles. And it's not very safe to put hydrogen in compressed cylinders. Because all you need is one good crash on the road and you've got a huge crater in the road from the explosion that follows. So they need other ways to store the hydrogen. One way is in hydrides. So they take the same tanks, or the fiberglass tanks, and they pack them with certain types of finely divided metal. And when you pump the hydrogen into it, it bonds with those metal. So that reduces its vapor pressure as it bonds with the metal. And that means that once you get the tank full, it only has a very small head pressure of maybe, I don't know, 2 atmospheres, something like that. It's just enough so once you crack the valve, it'll gradually come out slowly and feed your fuel cell. But you've got all that metal in there, and there's only so much room for hydrogen, so there's a limitation on how much hydrogen you can include. The other thing is liquid hydrogen. Right? That's what the space shuttle used, liquid hydrogen, liquid oxygen for its rocket engines. But liquid hydrogen requires refrigeration. Right? Most cars don't have that. They got air conditioners, but they don't have refrigeration because this is a cryogenic liquid. And that means that if you don't constantly refrigerate it, it's going to build up head pressure. And you have to have a built-in vent to release that. So if you just let your car sit out there over the weekend with a liquid hydrogen tank in it, you just filled it up on Friday, by Monday it'll all be gone. So that's enough stories about fuel cells. Let's talk about corrosion. What does corrosion mean? When we say corrosion, most people think of rust. And they would be right up to a point. Corrosion, in fact, is an umbrella term for any process that converts pure metal back to its oxidized form. For iron rust, that would be iron to iron oxide. For aluminum, that'd be aluminum oxide. For copper, it might be copper sulfide, right? Or copper sulfate. Buildings that have copper cladding on their roofs, they start out real shiny, right? That nice shiny copper color. But eventually they form that kind of a greenish dull color. That's from corrosion. But it's designed to corrode. So what it does is it converts copper to a combination of copper oxide, copper carbonate, copper sulfide, copper sulfate, and it forms that pretty color eventually, but it seals the metal underneath, right? That corrosion on the surface keeps further corrosion from progressing through the lower layers. That's why you want it to turn that color. And you can say that about any metal that's left out in the environment. It's an oxidation process. So the metal loses an electron like that. That would be a simple case of corrosion. This would be the half reaction for corrosion. And then that cation would be combined with some anion from the other half reaction. Okay, so this is what the corrosion of iron looks like. Steel, iron. It happens when water serves as the electrolyte. Right? And you get the anodic side is where you lose metal as the electrons are being transferred to the other side. And on this side, the half reaction is these Fe2 plus ions combine with oxygen. Let's see. Excuse me. Well, yeah, we could write out the entire reaction, but this is more of a more demonstration purposes. Right, we're not going to get into details here. And you can measure, you should be able to measure voltage here. Put one electrode on one side, one electrode on the other side, and measure a voltage there. I'm sure they have done that. So how do you prevent corrosion? Right? You've all heard me tell you about the Omni, a building that was built in Atlanta back in the late 60s, early 70s, that time frame. It was built with iron cladding on the roof, but it was particularly formulated so that it would rust really fast. and ideally seal the underneath layers. Well, what they didn't realize was Atlanta gets a lot of rain. Sometimes of the year it's as much as in tropical areas. And what happens is that rust isn't fastened really tightly to the underlying metal. So the water beats down on it and it washes that rust off, and it streaks across the concrete and leaves an ugly mess. Needless to say, that building is no longer there. And the architect who proposed it is probably out of business. But that concept of protecting the underlying layers is valid, right? It's a coating. But there's some metals that are better at it than others, right? One way is to just take that steel bucket and dip it in liquid zinc, called galvanizing. We still do it today. Anytime you go into a hardware store and you look for nails, you ask for nails suitable for outdoor usage, they're going to send you to the bin with nails that have this kind of a grayish surface appearance. They have been galvanized. They're coated with zinc. So when you drive that nail outdoors, it'll sit there forever and never rust. The other way is electroplating, right? You just set up a, now I'm talking about, actually I'm teasing you for the next topic, electrolysis. You run the reaction in reverse. Instead of making zinc into zinc 2+ ions, you make zinc 2+ ions into zinc on the surface of the metal. You turn it into a cathode and drive the reaction backwards to deposit zinc on the surface. We do that with chrome, right? Antique cars that still have chrome bumpers will coat chrome on their bumpers by running the reaction in reverse. The other thing you can do is alloy. Stainless steel originally was 35% chromium. And then, of course, the rest of it is iron with a small amount of carbon to make it steel. Well, what happens is this chromium was in sufficient quantities that at the surface of the metal, it is extremely reactive. It corrodes instantly. So if you get a scratch on the surface, it's sealed in a millisecond. So that's why stainless steel doesn't rust. The other thing is the oxide that forms from the chromium is about the same density as the steel underneath. Right? So they're compatible. In other words, it doesn't swell. Whereas iron oxide, due to its crystal structure on the surface of steel or iron oxide is a different density. It's lower density. So what happens is, as it expands, it forms and expands, it flakes away from the underlying metal and leaves it exposed. So if you go to some old farm somewhere and find a piece of equipment that's been left out in the weather for years, if it's still there, you'll find that all the rust spots that you see have rust flaked off either there or on the ground. And that's why iron implements rust really fast in the environment, because they do not seal. Okay. Oh, tailpipes. Exhaust systems on cars now. They experimented with stainless steel, but it's too expensive and too hard to work. Stainless steel is very hard. It's difficult to bend and it's difficult to weld. So they looked for an alternative, and they settled on aluminum. So they made an alloy of steel and aluminum, which made it light, but aluminum is a very active metal, and it will corrode rapidly. And what it does on your tailpipe is it corrodes and forms that seal. And it's just the right density. It stays put. And now we have aluminized steel exhaust systems. The last one I want to talk about is called Cathodic Protection. It was used originally when gas tanks were buried in the ground. they were steel tanks, right? And even if you painted them, they would eventually get pits in them, and the corrosion would find its way into the tank, and you get leaks, gasoline leaks into the environment. So the way to maintain the integrity of the steel tank, or a steel pipeline for that matter, is to use a sacrificial anode. Use a metal that's more active than the steel. Magnesium's a good choice. Zinc is a good choice. So what they will do is, this is one big electrolytic cell, and this anode corrodes and releases electrons into that wire. The wire is connected to the buried pipe or the gas tank or whatever's in the ground, and by supplying it with electrodes, it keeps the iron reduced, right? Just like we want it to be. In fact, you've got one of those, you've got an anode in your water tank, in your basement or in your crawl space, your hot water tank. It's made out of aluminum, and it will corrode over time and save your piping in the house from being further corroded. All right, I'm gonna have, I can't, I gotta cut that story off, sorry. Electrolysis. Electrolysis is very simply put, the galvanic cell run in reverse. And the way to do it is you just determine what is the voltage of that galvanic cell, that reaction, and you apply a reverse voltage of, if you want to stop the reaction, you equal the voltage. If you want to run it in reverse, you exceed the reverse voltage on the galvanic cell. That turns it into an electrolytic cell. And by definition now, the cathode becomes the anode and the anode becomes the cathode, because the cathode is always the cell where reduction takes place. Now, the stoichiometry of electrolysis is really very simple. You can measure, as you reverse the reaction, you can measure how much current is flowing through that wire. I mean, that's easy. And how long it goes. So what that current flow over time gives you is the amount of charge that's being transferred. Right? So here comes the Faraday Constant. If you know the charge that's being transferred, you can determine how many moles of electrons are being moved. Then you need the balanced equation to tell you, all right, these electrons, these moles of electrons produce how much metal in the process, for instance, if you're converting ions to metal. So it's just a series of dimensional analysis, conversion factors. So let's look at one problem. Let's see, that's not it. Here we go. So let's say we have an unknown metal M, and we're going to electrolyze it from solution. It's in solution as M with 3 nitrates. M and 3 nitrates. Okay, in solution. All right. We're also given that an amperage of 2 amps. So the current equals that A means amps. 2 amps is applied for 52.8 seconds. So time is 52.8 seconds. And how much metal was deposited? 0.0719 grams. So the mass is 0.0719 grams. Okay, question is, what's the metal? What do we need to know to identify a metal? One of two things. Atomic number, that's simple. But atomic mass will also get you there, because most elements have different atomic masses. So that's what we're going to have to go with here, but we can't find the number. So we need atomic mass. We need mass divided by moles. Atomic weight is what I say. We got mass right here. Right? We need moles. How many moles of M are represented by that mass? Okay, here's how you do it. First of all, you need to know what an amp is. An amp is equal to, in this case, 2.0 coulombs per second. Right? Otherwise, you can't make any conversions. Okay. So what we need to do is say, all right, we need a balanced equation to say, all right, how is that converted into metal? Right now it's an ion, right? And we know that each one of these is a -1. There. So that means with 3 of them here, this has to be a 3+, correct? So if M 3+ is going to be M solid, what do you have to do? You have to add 3 moles of electrons. So, how many moles of electrons do we actually have here? Well, we're starting off with 2 coulombs per second for how long? 52.8 seconds. Right? That gives you coulombs. But we need moles. So here it is. 1 mole of electron is equal to 96,485 coulombs. Coulombs cancel. Now we got moles of electrons. Okay, so mole of electrons are related to metal. How? For every one of these, it takes 3 of those. So that'll give you, that cancels, that cancels, that cancels. That gives you moles of metal. So now that's the hard part. That's the thinking part. Now all we have to do is the calculation. So we've got, oops, that's not my calculator. They all look alike. We've got 2 amps times 52.8 seconds divided by 96,485 divided by 3. So we got 3.65 times 10 to the -4. Moles of M. And there's mass of M. Mass divided by moles. So we just need to take this one and divide by that one. That one's already in my calculator, so I just need to punch in this one. 0.0719, and then divide by that one. 197 grams per mole. All right, so we look at our periodic table, and we know from left to right, top to bottom, the numbers get bigger. Right? Molar mass gets bigger. So let's see, there's 45, there's 88, there's 138, 227, too high, go back up to this line and go across. And there, 196.97 is gold. So we have plated out gold on some surface, probably cheap, or maybe even sterling silver. We put a gold plate on it to make it yellow shiny versus silver, which would corrode faster. So here it is, probably all worked out. Yeah, they're the calculations. So you got them there in hard copy. Okay. All right, we're just about out of time. Right. I'm going to keep talking, though. In fact, since I'm going to keep talking, I need a short bathroom break. I'll be right back. Okay, I'm back. All right. So let me erase this. Now you can use that process. You can use that process to determine if I want to plate out so many grams of metal on a surface, then you can work back the other direction and determine, all right, I'm going to need this many amps for this amount of time, and it'll give me exactly that mass of metal. That way you can economize on, say, if chromium is really expensive, you don't have to put more than necessary chromium on a bumper. Okay, so here we're going to predict the order in which metals plate out as the voltage is turned up from 0. Okay, remember what I was talking about. If the voltage for if the spontaneous voltage is a certain level, all you have to do is exceed in reverse, and you get that metal to plate. So what that means is, for these ions, they're going to plate, first of all, okay, I'm jumping ahead of myself. They're going to plate on the cathode, right? The place where reduction takes place. So with that knowledge, since we know that reduction is the key, there we go. The potentials, the reduction potential, will predict the order of plating. So the more positive standard reduction potential plate first as the voltage is increased. All right, so that one's going to go first. Then this one. You know, it just occurred to me that that may not be right. So if this is at 0.16 volts, okay, as an anode, it would run the other direction with a minus. Yeah, okay, that makes sense. I just had to convince myself. Since we're running this as a reduction, then the voltage has to run as if it were coming from an oxidation, running in reverse, right? So it would have to exceed that voltage in the other direction, right? So if you view these as the voltage required by the reverse would be sign change would be the negative 0.16 volts would run it in reverse, or 0.17 volts would run it in reverse. So as you increase the voltage from the other direction, then you get reduction in this order. So the more negative it is, the later it comes. There you go. So that would be the order that metals would plate out. And you could control it very finely. If you know this one, the difference between this one is pretty large. So you could increase this voltage into the, I don't know, halfway between those two. And you still only get copper, nothing else. And then once you got all the copper out, then you could crank it up a little bit more. It'd be kind of difficult to discern between lead and tin because they're very close together, see? But the farther apart they are, the easier it is to control and not get contamination. My guess is you're going to have lead and tin come out pretty close together. Unless your equipment is really accurate on voltage. All right, what are some commercial applications of electrolysis? Aluminum. Right? For the longest time, for decades, centuries even, aluminum was produced by chemical reaction. And I'm not talking about electrochemical reaction. I'm talking about just plain old kitchen pot reactions. Very messy, very difficult to separate the aluminum metal. And it was very expensive as a consequence. It was difficult to produce pure aluminum because aluminum is so reactive. The story is told that the monarchs of Europe, when they served their meals at state dinners, they would serve them with aluminum flatware because that was a sign of affluence. I mean, it cost more than gold. It wasn't until Hall, I forget his first name, developed the electrolytic reduction of aluminum from the ore that it became cheap enough for everybody to use it and for us to wrap our food in it and then throw it away. Purifying metals. Okay. When copper comes out of the ground as the ore, the pretty close to the mining site, there will be a preliminary processing unit that will clean up the ore and produce maybe a 99 or so % copper, which you think is really high. But for electrical purposes, it needs to be a lot purer than that. I mean, just for the wiring in your house, it needs to be 99.95% pure. And the best way to do that is to electroplate it. So you use, you put one plate on one side and a receiver plate on the other side. And in the solution, you have the electrolyte, and you oxidize the copper at a given voltage, oxidize the copper from the impure plate, and it migrates into the solution, and then you reduce it on the other plate. And then you get pure 99.99% pure copper. Metal plating, right? I already talked about that one. Chrome bumpers. Electrolysis of sodium chloride. Right? You just melt it. You melt sodium chloride and you electrolyze it. So what do you get out of it? sodium metal, and chlorine gas. Both very, very commonly used industrial stream feeds. Sodium for sodium hydroxide and bleach. Both of those are very common. Chlorine gas also for bleach, but it goes into many organic reactions. Okay. So this is what Hall's process looked like. Right? These carbon rods serve as the cathodes. I think. Let's see. The carbon is consumed because it produces carbon dioxide. Carbon would be oxidized. No, this is the anode, excuse me. This is the anode. And the cathode is at the walls of the container. Anyway, the nice thing about this process, and Hall developed this in his garage. At least he got started with it, and then when he got to college, he continued with it and found that it was cheaper to do it this way. And the molten aluminum that's formed from the process is denser than this electrolyte up here. So it sinks to the bottom, and then at periodic intervals, you just knock the plug off and drain out the aluminum. The big problem that Hall had was the melting point of aluminum oxide, right here, aluminum oxide, which is also known as bauxite. That's the ore. It melts at over 2,000 degrees. And if you're going to put all your energy into melting the aluminum oxide, it's going to be very expensive. So he tried to find ways to reduce the melting point, and he did. Found a natural mineral called cryolite. It's sodium aluminum fluoride. You mix that together with maybe 10.5% of aluminum oxide and the rest cryolite, and now it melts at 960 degrees. That's much more manageable. I guess the obvious takeaway from this is you need a good supply of electricity. The cheaper the better. So where do you get cheap electricity? Well, in this country, there are basically two ways. Coal-fired power plants produce electricity relatively cheaply, or hydroelectric power. The only reason hydroelectric power is cheap is because the government builds all the dams, and they charge the taxpayer for the construction cost. Then they can sell the electricity dirt cheap. So that's why you're going to find Alcoa built their refineries in southwestern Pennsylvania for the coal power. And there are some locations around the Great Lakes and on the Tennessee Valley. Now, the Tennessee Valley and southwestern Pennsylvania are primarily for the power, and the Great Lakes are primarily for logistics. So you have two ways to get your bauxite to the refinery. Both are the cheapest way, by water. If you can put something on a barge or a boat, the cost of transportation is orders of magnitude less than it would be for surface transfer on trains, for instance. So you could go up the East Coast in the St. Lawrence Seaway and down to the Great Lakes, and bam, there you're there. Or you could go up the Mississippi River, up the Ohio, detour off the Tennessee River, or you could go on up to Pittsburgh, and now you're into coal country. So enough said about that. Electroplating spoons. You can do that. Coat them with silver. Now, a galvanic cell, if you've got silver flatware, most people don't have silver anymore. But if you do, and it gets corroded over time, you can clean it up You just take a baking dish and you put aluminum foil on the bottom, and you put water and a little salt in it, and then you lay your spoon here. And the spontaneous process converts the corroded silver into silver metal, and at the same time corrodes aluminum. So the aluminum is the anode and the spoon is the cathode. But that's not an electrolytic cell, that's a galvanic cell to do it that way. Oh, here we are producing chlorine gas and sodium metal. No mystery there. Okay, I'm 13 minutes past. Any questions? Okay, well, let's see. This is our last class session. You've got your review video to do. If you have any trouble, working problems, or questions, I've still got my office hours, and I'll be keeping those. In fact, I'm going to keep my office hours through exam week. Right, so I'll be available then. And then if those don't work for you, just shoot me an email or text message, and we can set up a private session if you need it. Otherwise, just be sure all your exams are taken, all your homework's done, all your labs are turned in, because I can't grade thin air. And good luck in whatever you're going to do. Hope chemistry helps you get there.